So assignment 38, I'm going to combine 5.6 and 5.7. They relate to each other. The downside is that we're not going to be able to prove the fundamental theorem of calculus, but we're going to be able to use it. Okay, so we're going to talk about the fundamental theorem of calculus and then using that with definite integrals. So our essential question is, how can you use the fundamental theorem of calculus to evaluate definite integrals? So the fundamental theorem of calculus basically says this. If f is an integrable function, and if g of x equals the integral of f of x dx, then that means that if you take the integral, definite integral, from a to b of f of x dx, what you're going to get is basically g of the upper limit, g of b, minus g of a. Okay, so what the heck am I talking about here? So basically, let's think about this. So if I were to take the derivative of g of x, so g prime of x, that would tell me that I would get f of x. Because if I take the derivative, if I take the integral of f of x, I get back to g of x. Okay, so once again, if I take the derivative of g of x, I'm going to get f of x. And then if I do that antiderivative, or the integral of f of x, I get back to g of x. So when I have a definite integral, what I want to do is I want to have the antiderivative of f of x, okay, which is basically going to give me g of x. And then what I want to do is I want to take that antiderivative, that g of x, and I'm going to plug in the upper limit of integration, and then I'm going to subtract from that g of x again, or the antiderivative of f of x, and I'm going to plug in my lower limit, and I'm going to subtract them. Okay, so let me go ahead and do some examples with you on how this actually works. So I'll do one, and then we'll do some from your textbook. So if it says to solve the integral from 1 to 4 of x to the 1/2 dx. All right, so what I need to do is I need to take the antiderivative of x to the 1/2, okay, and that's going to give me my original function, the function that I originally took the derivative of to get to this, okay? And then to find that area under the curve from 1 to 4, I'm going to take that antiderivative, I'm going to plug in the upper limit of integration, and then subtract from that when I plug in the lower limit of integration. Okay, so first of all, the g of x will basically be the antiderivative, right? Okay, so the way that I would write this is that you could either write that g of x, right, because I'm trying to use an example here, or you could go straight to this equals, okay? Now, the antiderivative of x to the 1/2 is going to be x, add 1 here, so you're going to end up with 3/2, okay? And then it's important that you divide that out. Well, really, dividing by 3/2 is also like multiplying by 2/3. So that when I took the derivative then, if I multiply these two together, I get 1, subtract 1 from here, I end up with x to the 1/2. Okay, now there's always potentially a constant that was there, so we always put the plus c. Okay, I'm going to show you what happens to that. And then the way that it's written, and it'll be different in different places. I use kind of like a bracket to show that, okay, well, I need to evaluate this from my lower limit of 1 to my upper limit of 4. So really what this means then is that I need to do g of 4 minus, oops, sorry, I'm off the screen here, g of 4 minus g of 1. Okay, and then you'll see what happens with your c. Well, let me go ahead and show you. So G of 4, I'm going to go ahead and plug 4 in there. So I'm going to have 2/3 times 4 to the 3/2 minus, plus C. Minus, okay, and from that, I'm going to subtract now when I plug in 1, G of 1. So I'll have 2/3 X, 1 to the 3/2 plus C. Let's put this in parentheses as well. All right, well, this is really 2/3. Square root of 4 is going to be 2, cubed is going to be 8, plus C. And then from here, I'm going to have, well, 1 to the 3/2 is just 1 times, basically that's going to be minus 2/3. And then I need to distribute it to the C, minus C. So you can see what's happening to these C's. These are just constants that end up becoming opposites, right? Because we are subtracting the functions. Okay, so really the C's end up canceling out. So you don't need to repeat this every single time when you're taking when you're finding the definite integral. Okay, these C's are always going to cancel out. These constants are always going to cancel out. So basically what you end up with is 16/3 minus 2/3, or in other words, we get 14/3, which is 4 2/3. Okay, so that's how you basically apply the fundamental theorem of calculus so that you can solve definite integrals. All right, so let's do a few more problems. So that was really all 5.6. 5.6 would be us really proving and doing explorations with the fundamental theorem of calculus, but because we're limited on time, we are not going to do that, and instead we are going to now just practice working with definite integrals. Okay, so let's do some problems from 5.7. I think I'm going to do some of the evens. Okay, so from 5.7, we'll start with number 4. Okay, so you want to find the definite integral from -1 to 4 of 5x minus 2 squared dx. Okay, so basically what we want to do is we want to find the derivative of this, or sorry, the antiderivative of 5x minus 2, that quantity squared. Okay, and then we're going to plug in 4 and plug in -1 and find the difference between those two. So it's pretty straightforward. Okay, so first of all, let's start with my, the opposite of the power rule. Okay, so really this is going to be 5x minus 2 cubed. Now, I'm going to have to divide that out. So this is going to give me a 1/3 here. And then remember, if you were taking the derivative of this, you would chain rule it, right? So you would do times 5, which means I also need to get rid of that times 5 by really dividing by 5 or multiplying by 1/5. And then I'm going to remind myself that I need to evaluate that from -1 to 4 until I simplify it. Okay, so now these two multiply to give me 1/15. And I've got a 5x minus 2 cubed. Okay, I've left the plus c out because remember when we subtract these, the plus c's are going to go away. Okay, it's just whenever you don't know what that constant is that it's important that you put that plus c. Okay, so I'm evaluating this from -1 to 4. Okay, so a couple of things you can do. You can actually leave the 1/15 out, right? Because that's going to have to happen in both terms that both functions that I'm going to be plugging 4 and -1 into. So I can leave that out. Okay, and then all I need to worry about is this piece of the function. So that's going to be, let's see, 5 times 4 minus 2. Okay, that whole quantity cubed. And then I'm also going to subtract 5 times negative 1 minus 2 cubed, that whole quantity. All right, so I'm going to have 1/15. Now let's see, this is going to give me 18 cubed. Okay, and then from that I'm going to subtract. Let's see, that's going to give me negative 5 minus 2. That's going to give me a negative 7 cubed. Okay, and if you put that into your calculator, you're going to get approximately 411.67. Okay. All right, let's do another one. How about 8? Let's see, do I have 8 on here? So I'm going to evaluate from 20 to 50, 1 dx. Okay, well, this really becomes, let's see, the antiderivative of 1 dx. What did I take the derivative to get 1? It was just x. And now I need to evaluate it from 20 to 50. So basically that just gives me that 50 minus 20 equals 30. So I just took up one line with that because that was pretty short. Continuing on, I'm going to need more room than what I have on my paper, so I'm going to move to another sheet. We're going to do number 12. So the integral from negative 3 to 3 of the square root of 2x plus 10 dx. You know, and the first thing I would do is I would rewrite this so that I have an exponent as opposed to a square root. So I would actually call this going from negative 3 to 3 of the quantity 2x plus 10 to the 1/2 power dx. Okay, so taking the antiderivative of this, so I'm going to raise that power by 1. So I'm going to actually have 2x plus 10 to the 3/2. Then I need to divide that out. So I'm going to multiply it by 2/3. And then remember, I would chain rule this. So that means I need to actually divide out that 2 or multiply by 1/2. And then I'm going to evaluate that from negative 3 to 3. And you might see in your book or in other places, instead of having kind of this bracket, they'll have a line. It gets a little bit confusing. So I prefer having this little bracket, but you can do it either way. For me, I just worry that I might think it's a 1 or something else. So this just makes it a little bit more clear to me. Okay, and again, I don't need to put the plus c because remember what happens to the plus c, it basically cancels out when you're doing definite integral. So on your indefinite integrals, you're going to leave the plus c, but on your definite integrals, no plus c. Okay, or you can do it and you can watch it disappear each time. It's up to you. So let's see, here I'm going to end up really with 1/3 the quantity 2x plus 10 to the 3/2. And I'm going to evaluate that from negative 3 to 3. So now it's just time to plug those in. So I'll have 1/3 of 2 times 3 plus 10 to the 3/2. And then from that, we'll subtract. And again, I can leave that 1/3 outside or I can include it. I left it outside last time. Maybe this time I'll go ahead and I'll include it, realizing that it's the exact same thing. So it's 2 times negative 3 plus 10 to the 3/2. This is 1/3 of, let's see, 16 to the 3/2. This is 1/3 of 4 to the 3/2. Okay, square root of 16 is 4. We'll cube that. We'll get 64. So we're going to have 64 over 3. Over here, square root of 4 is 2. Cube that, you get 8. So I'm going to have 8 over 3. So this ends up giving me a 56/3, or in other words, 18 2/3. Okay, we'll do one more of these. So number 16, we're going to evaluate from 0 to pi over 3. Secant x tan x plus sine x dx. Okay, and you might see it like this. Okay, because this entire thing is being multiplied by dx. So doing the antiderivative. Okay, so the question is, what did I take the derivative of to get secant x tan x? That's just secant x. And what did I take the derivative of to get sine x? Well, I take the derivative of cosine to get sine x. Actually, I take the derivative of cosine to get negative sine x. So how do I get positive sine x out of that? I must have originally had a negative cosine x. Okay, and then this gets evaluated from 0 to pi over 3. All right, so filling in the differences here, we're going to have secant of pi over 3 minus cosine of pi over 3. And from that, we will subtract the secant of 0 minus the cosine of 0. Okay, well, secant of pi over 3 is really 1 over cosine of pi over 3. Okay, and from that I will subtract, I'll just go ahead and rewrite this. So this is really going to be, instead of secant of 0, it's going to be 1 over cosine of 0. Okay, so at pi over 3, let's see here. So pi over 3, thinking about that on my unit circle, right, that's, let's see, we've got pi over 6, pi over 4, and pi over 3. Okay, so I care about cosine here, cosine being the x value, so that's going to be, well, the units here, or the coordinates, are 1/2 root 3 over 2, but I really only care about cosine, which is the x value, so that's really just 1/2. Okay, so if I plug in 1/2 down here, that's really going to give me 2 minus 1/2. Subtract from that. Okay, so cosine of 0 is 1, and cosine of 0 is 1. All right, so 2 minus 1/2, well, that's 1 and 1/2. Minus, let's see, this is going to be 0. So basically, we're going to have 1 and 1/2. Okay, a couple of important things that I'd like to point out. One is talking about negative integrals. Don't forget about these, okay? So anytime that you have, the area between the curve that you have and the x-axis, maybe something like this. Okay, maybe I say here's A, here's B. Okay, so my area now between the curve and the x-axis, okay, is basically has a negative output, right? These are all negative. So for example, think about taking the Riemann sum, right? If you have these rectangles where your height now is negative and you still have some positive base, well, then what you're going to end up with is a negative area, right? Okay, so anytime that your curve is below the x-axis and that area between it is going to be negative. Okay, so that's important to remember. There's some, you can do there's some properties you can perform on these integrals, these definite integrals. So one of them is a reversal of limits of integration. Okay, so for example, maybe originally you went from A to B. Or let me switch that around. Maybe originally you went from B to A. Okay, which is kind of backwards, right? And if you're thinking to yourself, well, that'll probably end up giving you a negative. Well, that's true. And so one thing that you can do is you can just go ahead and negate the entire integral, and you can then switch your limits. So you can say, no, let's put the smaller one on the bottom, bigger one up top. So that is something that you are allowed to do. Otherwise, you could go ahead and solve it this way, and you're going to end up with that negative anyways. Okay, there are some, we can do a sum of integrals with the same integrand. Okay, so the integrand being the basically the function that you're taking the integral of. Okay, so if, for example, I'm saying, hey, let's take the integral from a to b of f of x dx, and let's say, for example, there's some letter or some point between a and b, such as c. So let's say that c is in between a and b. Then what I can do is I can break this integral up. I can say, well, let me first take the integral from a to c of f of x dx, and I'll add to that the integral from c to b of f of x dx. So I'm allowed to do that. I can break up that integral because it's basically got these two integrals, okay, are going, so for example, on your graph, maybe it looks something like that, and here's A, here's C, and here's B. So basically what I'm doing is I'm just taking the integral of first this area and then that area and adding it together. Okay, so that's possible. Let's talk about symmetric limits. Of integration. Okay, so you might have maybe, for example, like your sine function. It might look something like this. Okay, and you're going from, let's say, negative a to positive a. Okay, so this is symmetrical, right, with respect to the origin. This part is going to be negative. This part's going to be positive, but they're still going to be equal, just opposite, right? I guess I should say their absolute values are going to be equal. Okay, this one's going to be negative and this one's going to be positive. So basically, this is going to equal 0 when you take the integral of it, right? Okay, and this is of an odd function. There's that symmetry among the origin. Okay, however, maybe we have an even function. Okay, or maybe you have your cosine function, which we can consider an even function because it's symmetrical with respect to the y-axis. I'm going to do my best here to do a I'm having a challenging time with this. Let's just pretend that looks like the cosine function. Okay, where maybe here's negative a, here's positive a, and basically you're going to have the same area or equivalent areas on the left side of the y-axis and on the right side of the y-axis, right? They're going to be the same. So really, if you know one of them, if you just know half of this, then you can double it and get the other piece, okay? And so this is an even function. Okay, so let's do an example maybe of one of these. Why don't we do number 14 in that same section. So you've got the integral from negative pi over 2 to pi over 2. Okay, so right now there's going to be symmetry because we're talking about, let's see, this is 6 cosine x dx. Okay, so we're talking about the cosine function, and the cosine function is going to be symmetrical, and then we've got limits that are also equidistant or symmetrical, right, from the y-axis, okay? So that means that I can actually use the fact that this is an even function. I can use this to, instead of saying, well, let me just go ahead and find it from negative pi over 2 to pi over 2, I can just say, let me just find it from 0 to pi over 2 and double that. Really? So this is going to be the same thing as doubling the integral from 0 to pi over 2. Oops, of 6. Let me put 6 out there. Okay, and then there's one more thing I can do here, just like I did with derivatives when I'm doing antiderivatives, right? I can also pull out that constant. So really, this is going to be 6 and 2, that's going to be 12, times the definite integral from 0 to pi over 2 of cosine x dx. All right, so let's go ahead and do the antiderivative here. So the antiderivative, I'm going to leave the 12. Antiderivative of cosine, well, that's just sine. Okay, and I'm going to evaluate that now from 0 to pi over 2. Okay, so I'm going to have, let's see, 12. I'll leave that out. I'm going to have sine of pi over 2 minus sine of 0. So this will be 12. Let's see, sine of pi over 2 is going to be 1. Sine of 0 is going to be 0. So really that's just 12 times 1, which is